The curvature of a curve is a way to measure how fast the curve is bending at any given point. A straight line has zero curvature since it doesn't curve at all, and a very sharp bend has a very large curvature. The intuitive idea is that we're measuring how quickly we're changing direction as we travel along the curve. The tangent vector gives us the direction we're facing, and we can look at the change of the direction of the tangent at two different times to get a sense of how fast we're changing direction. But this starts to introduce some problems for us. If you think about a roller coaster, it's not hard to understand that the rate at which the direction changes depends on how fast you're going. And how fast you're going is related to the parameterization that you've used. We want the curvature to be related to the curve itself and not an arbitrary parameterization, which is where the arc length parameter comes in. The arc length parameter is defined by the shape of the curve and gives us the parameterization if we're moving along the curve at a constant unit speed. We're going to introduce a new idea known as the unit tangent vector. This is the vector that is parallel to the tangent vector that has length 1. We get this by dividing the tangent vector by its length. Remember that vectors are objects with both a direction and a magnitude. If we fix the magnitude to be 1, then the information in the vector is really just the direction. In fact, these vectors are sometimes referred to as direction vectors because of this. In the previous section, we noted that when the position is parameterized by the arc length parameter, the derivative has length 1. This means that under that parameterization, the derivative of position gives us the unit tangent vector. Since there is no forward or backwards acceleration as we move at a constant speed, all of the acceleration goes into changing our direction, and the curvature is the measure of how large that acceleration is. Since the derivative of velocity is acceleration, we are interested in the magnitude of that vector, and that takes us to the formal definition. Definition: if C is a smooth space curve, and S is an arc length parameter for C, then the curvature of C is the length of the derivative of the unit tangent vector with respect to S. The fancy-looking K is the Greek letter kappa. The more formal way to arrive at this formula is by working directly with the rate of change of the direction. The book does this derivation, and you should go read that part of the section to get the full treatment. This formula is great, except that it requires us to have the arc length parameterization, and we've seen that the arc length parameterization is sometimes difficult to calculate. If we have a general parameterization, then we need to do more work. There are two other formulas that you can use for the curvature when you only have a general parameterization. The first one is derived by applying the chain rule, and it's just straightforward algebra and calculus. The second one uses a more vector-based approach. There is a purely geometric interpretation of the curvature that's worth considering. We know that we can approximate curves near a point using the tangent line. But those aren't the only approximations we can use. It turns out that a curve can be approximated near a point by using a circle. We might even view this as a better approximation than a straight line, because we can mimic the curviness that exists at that point. There's a circle known as the oscillating circle that is the best circle to use at a point to approximate the curve. The roundness of the curve and the oscillating circle perfectly match one another at the point of tangency. Curvature is the reciprocal of the radius of the oscillating circle. The circle will have the property that at the point of tangency it shares the same slope and also has the same curvature. Arc length and curvature both have numerous applications. For example, on a roller coaster, knowing the curvature of a turn will allow you to calculate the acceleration that will be experienced at any specific speed, which tells you how fast the ride can go without injuring the riders or damaging the equipment. Unfortunately, those things are beyond the scope of this course, so we'll have to set them aside, but hopefully the idea of it will motivate you to look into this a little bit more for yourself.